finite element method, I will give a basic idea about what is basically design procedure and where this FEM will be mostly used, and what is during this design process. What we do it, we follow the numerical technique, numerical tools to solve this, and then we'll go to the what does that FEM means, what is typically. Then we'll see few applications, and I will give a small demonstration on finite element method on using an ANSYS. So that will see it. So basically, typical design process, and typically I'll discuss about mechanical engineering. The same procedure will be applicable for rest of the places. Basically, it starts with a problem definition. Problem definition means we are going to define what is exactly problem it is there. Means like just look at that in previous days we don't have any bicycle or kind of a device. So that time somebody has in their mind that he thought I need some device which will take me from one place to another place within a certain speed or kind of things. So that is what the vague problem we define it initial phase. So that is what it is called problem definition. Vaguely it is defined. That is it is defined this problem, and this vague problem will further it is processed, and then we are going to define certain parameters. Like if you want to design a bicycle or something, so we will decide what is the maximum weight it can carry. So that is one parameter. Another parameter, I think someone's mic is on. Yeah, can you hear me now? Yeah, can you hear me now? Yeah, so first of all we'll define in a parameter what is the maximum weight it can carry. That is one. Maybe in a 60 kg plus, maybe weight of the bicycle is 20 kg plus more weight. We may go for 100 kg as a maximum load it should transfer from one place to another place. Then another parameter will define as a speed. These parameters are typically called as a problem definition. This is what the way we define any problem in terms of numbers. That maximum speed will reach to 10 kilometer per hour or something. So this is what the way once we define this weight and speed as one parameter, then we'll look at different options available with us. Different options in the sense we may be looking for kind of a mechanism. What kind of a mechanism you want to use for it? We can go for a different type of mechanisms, like we can go for a bicycle belt drive also, we can go for a chain drive also, and so many other type of mechanism. And then that is what alternative solutions we are identifying. And once we get this, maybe one is mechanism as one alternative solution. Another is we can use different materials, that is another alternatives we may have. Then we may be using certain different configuration added together. So this is what multiple options available to execute your task is called as a synthesis. So in mechanism synthesis also we do it. We develop a coupler curve, so many things we do it. In that what we do, we change the dimensions of it. And based on that we decide, okay, if I change the dimension of crank, it is going to change me motion in this fashion. Motion pattern will be like this. So this is what a synthesis. Once we done the synthesis, then we'll finalize. We'll go for a chain drive. We'll go for steel as a material. Some part will be in plastic. Some part will be in aluminum. So that way, once we decide a certain model, some kind of parameters of this, that is what it will be taken to the model. Modeling will be in two parts. One is directly creating a 3D model using a CAD model. Another one is you can create a mathematical representation of that particular behavior. So that is another part of the modeling. Once we got this model, and we created entire model, then we'll apply certain boundary conditions for it. Boundary conditions means what is the maximum load it can sustain, what is the speed of it, all this. And after that, there are certain tools, and these tools are nothing but numerical techniques. These are all numerical techniques, and these techniques will be used to solve this. That is nothing but an analysis part it does. So this is what an analysis it will do it. Then once we done the analysis, then whatever the parameter we decided that maximum weight will be go for 100 kg, then speed will be something 10 kilometer per hour something. So this evaluation and check will help us to whether it verifies these numbers or not. If it is verifying this number, then we can go for further for manufacturing and testing, practical testing of it. So that is what it will have in two ways. One is directly move to the prototype design. If everything goes fine, and if it is not, then you go on changing the dimensions of it. Either you change the dimension, either you change the material, or kind of things you can do it. Again, you go on doing this particular loop. This is what an and this is what it is called as an iterative loop, which will continuously move it from iterations. That is what iterative loop. And once we get the answer, how many times we need to do it? So we should get the answer as in a yes here. That is what in a then you can develop in a prototype. Once we get the prototype, because whatever the model we defined it here, has started with a certain assumptions. Assumptions means what we are doing, we are assuming certain parameters like the beam bending theory is there, your fluid flow problems is there, the Newton's law is all the time it is following, and kind of things we assume it. But in practical it doesn't happen in most of the cases. So that's what practical testing is the most important. That is what we develop in a prototype. We design the prototype, test it, and during this testing, there is a possibility it may fail again. There is no answer will be there. This is not going to satisfy these conditions. So then this is not going to meet these criteria. Then again you need to follow another loop of iteration. This is second loop of iteration. And then once it is yes, then we'll go for a final design, then manufacture it, market it, and send it to the end user. So during this entire process, most of the time we may vary. So FEA or any CAD software will help me in all the stages. So these are the stages through which this design activity works. So in these stages, only these places, modeling, analysis and evaluation check, only these three places, this FEA analysis, CAD modeling, this will be helpful. So it will never help you to generate any new ideas like in synthesis we do it. It will not help you to develop in a practical prototype. It can give you the model, and that model will be given with either 3D printer or any machining process something. So this is what the three stages of the design will be uses this finite element as a method. So that is what basically restriction for this FEA analysis. So whenever we do a problem analysis, what the way we do it? So there is a mathematical model, there will be a differential equation and kind of things, and then you are going to solve it. So basically, if I say in a spring mass damper system, my equation will be something mx double dot plus cx dot plus kx is equal to some function, and then I will go on doing an integrations. 2 times I will get the integration, I will get the fx as a function of t. So this is what the way analytical solution will do it. We do an integration over the time. This is one time, another time, like this we do it, and this way we will get the solution for it. And this way most of the phenomena nature will be represented using differential equations. So this equation contains, when we are solving such problems, it contains 2 parts. One is homogeneous part. In homogeneous part means I am assuming my equations are like this, plus kx equal to 0. This equation is called as a homogeneous part, and this equation is called as a particular integral or non-homogeneous part of it. So how to solve it? We combine this, we superimpose and kind of things, we do it, and we done. We most of the time we follow this vibration techniques to solve this. But before moving to the differential equations, before moving to the FEA, so basically all the phenomena in this nature are defined by a differential equation. Differential equation represents rate of change of certain variable. Certain variable means here it is if I take a parachute or something example. So I just leave the parachute from a particular height and then it is moving in downward direction. What exactly it is going to happen? In this case, I am going to apply the downward force. That is what due to the gravity this force will be. There will be another force which is going to move it upward, which is opposing the motion. That is what we call as a lift force. And then there will be some inertia force which will follow m into a, that is force equal to mass into acceleration. And this all parameters are changing with respect to time. That is what this velocity changing with respect to time, and then acceleration is changing with respect to time, kind of things it is going to happen. So that is what the way you have to define, and that is here it is dv by dt means velocity changing with respect to time, and this is represented by this equation. So this is called as a change in the particular parameter with respect to some independent parameter is called as a differential equation, and that differential equation has two ways you can represent. One is ordinary, where only one single independent variable is there, and some are partial. Like in a simple example, you take it, I have on a plate and I am going to heat it, maybe here it is a 200 degree, it is 100 degree, here it is on a 200, okay, again it is 100. I want to determine the temperature at this point. So this plate has an x coordinate here, x direction as well as y direction. So whatever the temperature at this point is only depend on x variable as well as my y variable. So that's what I can now write. Temperature is depend on x also, temperature is depend on y also. It is a second derivative because it does follow second derivative, and then I can write an equation. This equation is called as a Laplace equation. So this is dependency is on two variables. That's what it is called as a partially it is depend on x, partially depend on y. This temperature variation. That's what it is called as a partial derivatives, partial dependency. And this is ordinary is only one single independent variable. So we'll now look at, so this is what basically a difference, ordinary differential equation, only one t parameter is there, here it is in a two parameter, x is there, y is there, kind of things. And when we want to solve such equations, what way we solve it? So in this ordinary we have gone through so many examples during our maths subjects. But here this treatment is to be needed to be done in different fashion. And most of the problems in the universe are follows partial behavior, partially depend on some of the parameters, independent parameters like this. We'll take a simple example. There will be two types of problems. One is boundary value problem, another is an initial value problem. We'll just look at the initial value problem first. Initial value problem is, this is a spring mass damper system. In this spring mass damper system, there is a mass, there is a spring and damper, and it is fixed at the ground. So when we are going to given some force onto this, so it has some initial condition, okay. This particular mass has some initial condition at x at time t is equal to 0. I want to do the analysis with respect to time. That's what it is called as initial. We are going to define an initial configuration of the system at time t is equal to 0. That's what is called as an initial value problem, because you are going to define at time t is equal to 0 what is my displacement, maybe in x0, maybe what is my difference velocity, that is x0 dot something. So this type of problems are called as initial value problems. So what does that boundary value problem means? Just take this problem. In this problem, there is no change in the mass of it, no change in the spring stiffness. There is no change in the viscous damping and kind of things. Only the x is varying with respect to time, and that's what it is called as time dependent problems are called as initial value problems. This is what the way it is represented. Now we'll look at the boundary value problem. In boundary value problem, just take an example of beam. What is going to happen in this beam? Here my boundary of this particular beam is something at this x equal to 0 is here, and here it is an x equal to L. And I'm going to look at deformation pattern at all these points. So I'm going to determine the force, I'm going to apply the force here, and it is going to deform in this fashion, something. Okay. So that deformation with respect to x I'm going to determine. But at this point, my displacement at x equal to 0, my displacement is 0. At x equal to L, I don't know how much amount of deformation is there. Also, I am going to put up one more condition here. At x equal to 0, my slope of deformation is 0 because it is showing in a straight line here. So this is what the two conditions that it show, and you are looking the solution of the problem within this boundary. So that's what it is called as a boundary value problems. Okay. So just like take an example of plate. Okay. I am going to fix it here. I am going to vibrate this plate within a certain force, that is f of t force. And now it is depend on time also. Okay. And also it is depend on x, or all x location my deformation will be different. So in that case, so this represents an initial value problem. Okay, as it is your force is varying with respect to time, this represents an initial value problem, and this is going to represent as a boundary value problem. Then such type of problems are called as initial plus boundary value problems. Okay, combinations like a plate is vibrating and you want to determine the shape of the plate at particular time instant. That sort of problems are called as boundary value plus initial value problems. So this is what in a way it is represented within a differential equation, and this is a fourth order equation. So we can just go through the strength of material point of view, and we can understand how these equations are arrived at. Okay. When we are solving such problems, there are two techniques. One is analytical technique, another is a numerical technique. In analytical technique, what we do analysis within a simple treatment. I have an equation like an mx double dot something plus kx equal to 0. I will now do a double integration with respect to time, and I will get the solution of this. That is x equal to some function of t something. So this is what in a treatment is called as an analytical. In numerical, what we do, we divide this entire domain into a small chunks, and we assume within this domain my behavior is something linear, maybe a parabolic or kind of things, and then we combine this. That is what in a divide and rule kind of technique we use, and that is what a numerical. And this numerical technique is approximate. It doesn't give you accurate solution. Here it gives an exact solution, because your treatment is perfect enough, which will give me an exact solution. Also it gives me a closed form solution. So this all comes under the analytical part. In approximate, you are assuming. We have starting with a certain assumption. This is what an approximate solution we will get here. So we'll now look at what is the way I will just give a brief comparison between numerical as well as analytical technique. There are many practical problems which cannot be solved by exact solutions. That is what we need to rely on certain numerical tools, and that is what the way we can now do. One thing, you can discretize. That is, you need to get the solution at discrete points. Those points are called as nodes, and these discrete points is now later connected with my kind of an interpolation function or kind of things, and then we'll solve it. Okay. So we'll now look at the comparison of this. We'll just take a simple example, modeling of falling parachute. So this parachute person is now just dropped from airplane, and then now you want to do the analysis. What is the maximum velocity it gains and all these things. So what is the first technique into this? We have learned it in the first year itself. That is, first technique is that you need to go for a free body diagram. So that is what a free body diagram. First input to the system is dropped from the particular altitude, that is high altitude. So then output, you are looking for a change in the velocity, how much it is going to happen, how the change velocity is going to change, is going to, that you want to determine. This is what a system. This is system. Then whenever you are doing an analysis of any system, so there will be all the time some input will be there and there will be some output. And this system is nothing but a system model or any mathematical model represent. This model represents connection between your output and input. So output is my velocity, input is my force. So this is nothing but my transfer function, I can say. We have seen it in mechatronics point of view. So that is what the way it does. So what is the first step? First step is to create a free body diagram and then start applying the forces on it. What type of forces will be there? There will be one downward force, that is what due to the gravity. Another force is upward force, which will oppose this motion. So that is what air resistance. This upward force is all the time it should be negative. So that is what a minus CV, I can write it here. Downward forces m into g. Then we can now put this and equate it with the total net force acting on it. That is the way we can do it. This Fu is nothing but a minus CV plus m into g, okay, divided by m will give me an acceleration. Okay, acceleration, that is what an acceleration it is defined. And this acceleration I can write it dv by dt, that is change in the velocity with respect to time. And then now I can write mg minus cv upon m, and then I can get one equation, dv by dt is equal to g minus c by m into v. So what this indicates? This indicates behavior of your parachute when it is dropped from certain height. Okay, what is the change of velocity is going to happen with respect to time? So I may have a time step which is equal to 1 second, and I can go what will be the velocity of time 1, what will be the velocity of time 2, then 3, like this. Means it is going to have with respect to time that velocity, initial velocity 0. So it will go on increasing and somewhere it goes on to the maximum, or may go straight also. So we want to see what is the maximum velocity it can achieve. What is the velocity, whether it reaches to the infinity or something. What is the way it behaves. So that behavior you want to identify it. So for that purpose, what you can do it. So this is the first order differential equation. So it cannot be solved by algebraic manipulation. You can use an analytical solution. You can take an integration of it. After integration, you will get this solution. This is what called as an analytical solution. Sorry. This is an analytical solution for your problem. Means after integrating once, I will get an integration on the both the side. I will get dv is converted into v of t, and then I will get g by m 1 minus c 1 minus e raised to something. So this is what it is called as an analytical solution. So now we'll look at this analytical solution, how it happens and what is the behavior of it. So if I put this all parameter, what is the g value, then m value, then c value, all these values, 68.1 is weight of the person, 12.5 is drag coefficient, 9.8 is nothing but a gravity, and then we'll determine the values, that is at time t is equal to 0, my velocity 0, as we have started with a 0 velocity. Then at time t is equal to 2, I got a velocity 16.4 or something. So now I can, if I put this time at infinity, what it indicates, it reaches to the maximum velocity at 53.39. That is what it is called as a maximum terminal velocity. Why it is called as a terminal, or why it reaches to the only that much velocity? Why it should not go on increasing? The reason for this is your parachute. It is taking in downward force. There is one more force is upward force. So if this force is coming somewhere 100 Newton and upward force is also coming to 100 Newton, both will get minus, and net force acting on your body will become 0. And that net force, as net force is acting on the body 0, your equation is mass into acceleration. Mass never be in a 0. So your acceleration becomes 0. Acceleration means your change in the velocity, that is v2 minus v1 divided by time. This and this is the same, and that's what I can get in a constant velocity. So that is what the way you can reach to the maximum terminal velocity. When your net force is 0, your velocity is constant. This is nothing but a rule, that is Newton's first law. It tells whenever there is a velocity is constant, there is a force, whatever it is acting is 0, or that is vice versa kind of things. So once we got this, now we'll look at how to do this numerically, how to treat this numerically. This is what an analytical solution we got it. Now this is what in a differential equation. So this is differential equation means what? So dv by dt, can I write this dv by dt? But this means if I look at into with respect to time, this is my v and my equation is like this. I can now have 2 points onto this. This is 1, this is 1. This is at time t is equal to 0, this is t1, and then I can join this within a straight line. Okay, this is what an approximate solution I can get it. So this is my v0 and here it is in a v1. So can I write this differential equation v1 minus v0 upon t1 minus t0. So this can be converted into limit as time delta t or what are the time step tends to 0, this becomes your dv by dt. Okay, so this is nothing but basically a definition for your differential equation. So this is now, I will now remove this limit. Okay, we learned this limit into the 12th itself. So this, if I remove this, then it will give me a finite steps. If I put this limit, that indicate it has a very small step, which is going to tell me a direct tangent of it. So that is what in a derivative is called. If I remove this limit, then it becomes a difference equation. So now I can write this differential equation difference equation delta v upon delta t. That's what this is approximate. That's what this symbol is now represented there like this. So this is now one step. This is my second step. Then I can differentiate. Now I can convert this. I will now replace this dv by dt with this difference equation, and then I will write your equation once again. And you know the initial velocity, starting velocity 0, that is v0 is 0 here. You know this, and only you know the time step. Unknown is only what will be the velocity at the next time step. So that is what it is called as. So now I can simplify, I can rearrange it, and I can get this velocities. So this is my initial velocity plus the rest of the parameters we know it, and we can quite easily determine a velocity at next time step. And this is nothing but the way we do it in approximation. Okay, this is what the approximate slope is this, and your true slope is this. So that's what, if I take a slope here and I am going to determine it, this is nothing but an error happens, and that's what this error is due to the approximation. What kind of an approximation we are going to do it? So approximation we are going to do it. These 2 points you are joining within a straight line, but they are not straight line, they are having a curve. Okay, so instead of curve you are assuming a straight line. That is what nothing but we do an approximation. Okay, so now we can take on steps and we can solve it. So we have now 2 equations. One is your previous equation v of t, that is analytical equation, this analytical equation, and this is your approximate equation. Now you want to compare these two, which one is going to give me a better result or something. So here I can now put up on a time step 2 second, 4 second, 8 second like this, and I can go on determining it. So when you want to minimize this error, what is to be done? So this time step should be very small. I can go for a smaller and smaller step size, and I can get a more and more accurate solution. But as we are going for a smaller step size, means we need to do so many calculations. It needs a more computational efforts and more calculation it has to do it. We'll look at how it is to be handled. So this is what an analytical solution. This is what a numerical solution. Okay. In this numerical solution, what we do it. So this is equation for your analytical. This is equation for numerical. Now we will compare the results for this. We will keep in a delta t at 2 seconds. Here it is the result at 2 seconds. I got 16.4. Here I got a 19.6. What that indicates? Whatever this difference is due to my step size 2 seconds. Okay. And if I reduce the step size, I will get a better accuracy. And same way you can observe it, that difference is increasing in next time steps like this. Okay. So that is what the way you can go at. And then if I reduce the step size to the 0.5, here it is a 2 seconds. If I reduce to the 0.5, you can observe that your answer is now 17.6. It is more near to the 16.4. If I still reduce the step size, I will get a 16.41 here, and here it is in a 16.4. And this is what for 0.01 step size, I will get an accurate result. Means it is still there is an error, but I can say it is in a better accuracy. I can get it here. So this is what the way you can compare both the results. You can do it. This is what the way most of the numerical techniques or most of the FEA solvers and all this does the work in this fashion. So when we are solving the problem, what we have done, we divided this into small steps. So divide and rule, that is what the principle we use it. So when we are solving the problem, first we have seen an analytical method. Another is a numerical method where we do and divide and rule kind of things we do it. And then last one is experimental methods. One is analytical, then numerical, then experimental method. Experimental is more realistic method. It gives a realistic approach. Okay. Here it is again started with a certain assumption. It gives 100% results because it is based on some equations. This is what an approximate method, and it is assumptions are made like it is having some curve, but we are assuming it is in a straight line something. That is what. Here in both the cases you don't need a prototype. In this case it is a prototype is needed, practical testing is to be done, all these things is to be do it, and minimum 2-3 prototype are to be tested, all these things we need to do it. So this involves too much cost, and that's the reason this has given a birth, because this cannot be solved for all type of problems. This involves too much cost, it takes time, so many things it is needed. But a numerical method you can rely on computer itself. We need to have some tools, and maybe in the programming you can do, maybe you are going to do it in kind of things like you can use an ANSYS kind of softwares, and we can use it. So in this numerical method there are different methods available altogether. So we have learned so many methods like a Runge-Kutta methods, root equation, something. So when we combine these tools within a certain software, then it is called as an ANSYS type of software will take a birth of it. So here in this finite difference method, there is one table is called as a finite difference. The next is a finite element. In finite difference, we can easily solve thermal problems, fluid problems, all that CFD type of problems. We can quite easily solve it. Then finite element, you can use in a linear, non-linear analysis, then buckling analysis. You can do in a thermal, dynamic, fatigue analysis. So many things you can do. Even you can have a rigid body analysis, flexible body analysis. So many things we can do it in this case. And then there is a method called as a boundary element method. In this boundary element, what it happens in finite element, when we are doing an analysis of beam, we assume this boundary and this boundary doesn't change. Means this x equal to 0 is there and x equal to L is there. If I take a balloon or something, this type of balloon, and I'm going to put the air inside it, boundary of this balloon is continuously changing as I'm going to increase more and more pressure here. So this is going to change like this, and again next time step the size will be something more, and this boundary, what are the boundary, that condition of the boundary is continuously changing, and that's what this is, what this method is called as a boundary element method. And this is most useful in all vehicles where this noise you want to reduce it, you want to analyze the acoustics of your theater or kind of things. In that case, this technique will be a much more useful and use. And last one is in finite volume method, that is typically CFD techniques. Okay. So we'll now look at the how to do this problem solving. First of all, divide. Okay, small chunks, which we seen it in our simple example. Then do an analysis to the elemental way, create an elemental equation, then assemble all these elements, then solve it. So these are the steps through which it works. So that is a complex problem solving technique. This technique can be used for any other normal life also. When we do in the class also, we use this technique for handling the students. We divide the students, we separate the students and handle them in smooth fashion. That is what we do this technique in most of the cases. So in finite element method, this technique which I will give a brief basic idea about what does that, how does finite element has taken about. So initially we have seen in a numerical technique. So this is, I am taking in a beam problem, okay, and I am going to solve this beam just a bit. So this is my beam. I want to solve. Beam solving means I am going to apply the force here, and this is x equal to 0 and this is my x equal to L, and ultimately you want to determine the deformation pattern like this, and ultimately I need y is equal to some function of x. So this is the solution you are looking for it. So in this case what we can do it, so basically we can first, you can take this is your entire domain. I can divide that domain into multiple points. So this is what it is called as a discretization. I can now separate this particular one single element. I can now put the behavior of it. So that behavior is represented by d2y by dx square is equal to m by e as equation. This is what in a beam bending equation. Then I will now go on determining, I will now formulate two equations for this node, two equations for this node. And then I will now solve this. When we are solving such problems, I will put up on a boundary conditions at this is fixed here, this is fixed here, and force is applied at this point. So I will now get the solution at this one, then I will get the solution at this point, and this point. So this is my deformation U2, then U3, then U4, I got it, U5, U something. I got the solution at this point. I don't know the solution between this point and to this point. So that's what this type of technique is called as a finite difference method. This is what in a finite difference method. So but in later stage it is observed, if I go for this step size is a very small, delta x step size is, if I take a smaller, I'll get better results. But in between I can't get the solution. So I can now assume this is what deformation is from this point to this point it is 0, from this point to this point it is a point U2, then from this point it is U3, like staircase type of effect you can get it. But we don't know whether it is connected by straight line or some curve or something is there, some may be there. So we don't know. So that is what we need to formulate a certain equation between this. That's what it is called as an interpolation function. You have one value here and another value here, and you are connecting this value with a simple straight line equation, means it is an interpolation function. And that's there the FEM comes into the picture. The FEM, what it does, it will take and divide this. It uses the basic principles of all finite difference method and add it with an interpolation function. Okay, and this will give a birth to the finite element method. And that's what this method is also called as a piecewise interpolation. This is my one piece of information I'm going to connect with a straight line. This is another piece of my element I'm going to connect with a line. So that is what the way you are going to connect with this with an interpolation function, and which gives a better result than finite difference method. And also it gives a better result with a lesser number of computation, because when you want to get a more accuracy, this in the stair type effect will not be a much more useful. So that's what finite difference will give a lesser result. But as I include this finite element, finite difference method with interpolation function, that will create a new method that is finite element method. So that's the reason this finite element method is called as a piecewise interpolation tool, piecewise interpolation mathematical method without a boundary is assumed. And because that element move like anything, that is what it does. Then it is an approximate function is assumed to be a represent solution of each element. That approximate function may be in a straight line, maybe in some parabolic curve, maybe in a cubic curve, or kind of things. That is what. Then complete solution is nothing but a solution of this all ultimately all elements. This is one element, then second element, third element, and total solution will be this is one connection, this is my another connection, then this is my third connection. So this represents a complete solution of your problem. That is what it is called as an assembly. When you are assembling it, you need to make sure that continuity between the element. This is my one element and this is my second element. I need a continuity. My displacement should be the same at the nodal point from in both the element. If they are different, there is no use of getting such solutions. It will practically, it is not happening the way it is. That's what you need in a continuity. That type of continuity. If I am ensuring displacement as in a continuity over this particular point, then it is called as a C0 type of continuity. If I am ensuring slope type of a continuity, then it is called as a C1 type of a continuity. And if I am going for a higher order continuity like a curvature or kind of things, then it is called as a CT type of continuity. So, well, what type of analysis we can do it? We can do a static analysis, we can do a dynamic analysis, we can do a motion analysis, so many things we can do it. Then optimization also you can do it using finite element method. So I will give take a few examples of case studies, and then I will take a direct example on ANSYS. Sir, how much time is for me? Sir? Hello? Can you hear me, sir? Yeah. Okay. Can I take half an hour more? Yeah. So, here there is a few examples. I will tell you one case study. So there is a spring design. Okay. When we are designing a spring and manufacturing it, so that what are the measurement, we do it in practical way. Okay. So here is a Nastran type of solver is used to solve the problems of this FEA, problems of this spring. So here it is a non-linear static solution is done, and what is the use of it? So when we are manufacturing this spring, practically testing it, getting the results whether it is correct or not, then again replacing that spring with another one, it takes too much time. And to avoid this, so we can do directly, we can simulate this entire environment onto the computer using this Nastran solver. And what advantage we got? We reduce the cost of analysis. We minimize the design time from 10 days to only one single day. That is what the advantage. That's the reason this is FEA is having an advantage. One more example I would like to tell, because this PPT I am going to share to you. Anyway, you can use that PPT in later stage. So when there is a heat exchanger, most of the time you can see such heat exchanger in sugar factories or somewhere. Okay, what is the use of heat exchanger? It takes a heat, it heats to that gas heater will be there, or some combustion chamber will be there, it will heat it, and it will now generate maybe in a molten metal, or it will be used if you are using it into a foundry or somewhere. So what is it is this heat exchanger is designed using an FEA technique, and we have minutely changed the dimensions. Whenever I need it small change, I can do it, but practically it is not possible. And that particular design has a given advantage. This design will give an advantage over previous design. What kind of an advantage it will give? It reduces the 38% of the gas consumption. It reduces the CO2 emission by 800 tons per year. So that is what too much saving you are going to do it. And also it has increased 200 kg of melted aluminium that is used in foundry, melted aluminium per hour kind of things. So this new effective kind of designs you can do it. This is one example I told you. Similar fashion you can find so many such examples. So this is one more is a turbine blade example. You can just go to it. Okay. So finite element is nothing but a piecewise solution. Pieces, you are going to look into the pieces, then these pieces you are assembling it and you are solving a complex problem. So basically step is to first of all create a model, mesh it or kind of things, apply the load, then define the boundary conditions, then define the element properties, then assemble all the stiffness matrices, solve it, then calculate the stresses and deflections and kind of things. Okay. Then these are the steps through which it works: solution phase, post-processing phase, pre-processing phase, all this. Okay. So at the back end, how it works, that is the most important. We'll take a simple example of bar. Okay. I will tell you how this mathematical tools or maths part it will work, and then we'll move towards the ANSYS demonstration. So this is a bar. It is force is applied at one end, that is what an external force is applied. This is a fixed state. When we apply a force onto this, it is going to deform it, and then that model you want to analyze it. What way we can do in FEA? We can divide this into small elements. This is my first element, this is second element, and third element, and then these nodes are given in numbers 1, 2, 3, 4. So these nodes, it is assumed these nodes will have only one direction deformation. Assume it is not actually it is going to happen. Each node is having only one deformation, that is what in the axial direction. But in actual practice, if I take any point into the space, it has an x deformation, y deformation, then z deformation, rotation about x, rotation about y, and rotation about z. Altogether 6 DOFs will be there. Rest of the DOFs are not much more significant, as it is I am going to apply the force on this direction. Deformation will happen in this direction. Deformation will not happen in perpendicular direction, and whatever the deformation happening in perpendicular direction is very less. If it is deforming 5 mm, here may be 5 micron or something, which is negligible. That is least interested. So that's what can be neglected quite easily. And we can assume each node is having only one DOF, that is degree of freedom. Okay, one DOF, and altogether we have 4 nodes. So obviously I will get a total model DOF is 4 degree of freedom. So now what is the way we determine deflection? That is in a simple formula, delta is equal to PL by AE for a simple bar. Okay. Then now we'll take a single element, we'll separate out this element, what are this element, and we'll determine equations for it by using a free body diagram technique. Okay, so we'll take a single element out of it, and this is what a single element I got it. There will be a deformation on one node, then deformation on the second node, force on this, and kind of things. Now I can formulate the equations, equilibrium equations for each node. So this is represented, this equation is represented for first node, this is one equation, this is represented for second node like this, and then now I can combine this. Okay, this is what the way U1 you got, U2 here, U1, u2 kind of things. Now it has only unknowns, two unknowns, u1 and u2 and f1 and f2. Now I can represent this into the matrix form. This is what it is called as an elemental equation. This is what represents an elemental behavior. Means it represents 1 minus 1 minus 1 1 something. So this is this 1 2 these numbers you can give it, and you can say this is elemental equations. And this elemental equations, if you look at, this is what in a stiffness matrix it is called, then displacement vector it is called, then force vector it is called. You can just represent into the matrix. Why to do into the matrix? There isn't a specific reason for it. So when you are solving any algebraic equations, ultimately what you are going to do it, as you are going to solve algebraic equations, if I have a more number of algebraic equations, you will find it very difficult to solve. And that's what there is a technique called as a matrix method will be used to represent those algebraic equations into the matrix form, then use in a technique Gauss elimination, Gauss seidel or any kind of a technique and solve it. So, well, now we have only one element we have taken, okay, and we assume the behavior of this element is the same as element number 2, element number 3. So it represents, it is nothing but a kind of a rice when we cook it. We only pinch one single piece of it, but we never go for pinching each and every particle of it. So that is what the way this, because body is entirely moving within the same principle. So anyway it is divided, means principle will be the same and can be observed in each and every element of it. So now I can have one equation, two equations for this, another two equations for this, then another two equations for this. Okay. So here you can see this is what in a deformation u1 here, then u2 here, then u3 here, and then u4 here. So here represents u1 and u2 behavior can be represented by this equation. Behavior of this is represented by this and this. So one thing it is observed, this is u2 equation, this what are this u2 equation, and here also it is a u2 equation we got. So which represents the same behavior, means one of these two are nothing but the same, they should be added. So that's what at this particular point deformation in this element, that is one number element u1, I will say it is 1, and deformation in this element u1 element number 2 is the same, and that is what it is called as a continuity you are going to maintain. What type of continuity you are maintaining? Displacement continuity over the element 1 to second when I am going to move it from one element to another element. So this is what the continuity, which is called as a C0 type of continuity. Okay. So when you are going to solve in a beam type problem, you need to go for C1 type of, then C2 type, and maybe you are going for a higher order. The same is it is observed in the third equation. So third element, third node. So this equation and this equation is the same. So now you can assemble it by adding all these equations, and you can get the final equations like this. Here you will get an addition 1 plus 1. Here you will get an addition for this 1 plus 1. Because this node number 2 is a common. Node number 3 is common between 2 and 3 element and 1 and 2 element. Yes. Okay. So now we got this 4 equations, as we have 4 nodes, and how many unknowns are there? We don't know u1, we don't know u2, then u3, u4. Also you don't know how much amount of forces acting on it and anything. Okay. Ultimately this is a 4, this is a 4. Altogether 8 unknowns are there in the equations. And how many equations we have? We have only 4 equations with us. How can we solve it? So that's what we need to reduce these unknowns. Maybe something is missing which we have not taken into account. Okay. So we'll now, this is what it is called as in a global stiffness matrix. This is a global displacement vector, and this is a global force vector. And these are the system properties. Okay. And then we can apply the boundary conditions on that. Okay. In this boundary condition, what it is assumed? The displacement of node 1 is 0. This is what a displacement u1 is 0. So here this U1 is now replaced with a value of 0. And then if I apply the force onto this, so obviously this F4, force on the node 4, what are the force you are going to apply P here, that is replaced with this F4. Okay. So how many unknowns are left? So only 6 unknowns are now left for us. Okay. So now whenever you are going to fix it, obviously there will be a certain reaction it is going to happen. That is what it is called as a reaction force. And that's what this F1 can be represented as a reaction force. Okay. And this F2 and F3 are internally balanced. That's what your entire structure is a static. So that's what I can now make these 2 points 0, and I can quite easily say my solution is like this. This is R is unknown for us, U2, U3 and U4 are unknowns, and the rest of the things are only we have 4 equations and 4 unknowns. So you can quite easily solve it. Okay? So this is what the way you can convert your any complicated problem into discretize it, then assemble it, and then solve it. So this is what a reaction force which is equal to applied force. Now there are plenty of the techniques available to solve such problems. So 4 unknowns, 4 equations. Maybe you can go for Gauss elimination, maybe you go for Gauss-Seidel, value decomposition kind of things, and you can get the deformations U2, U3, U4 quite easily. So this is the way you can. This is the entire way that FEA part works, and same technique is used in any of the CAD FEA solvers. Only the method may be different. They may be, some people may be using a Gauss elimination, some people may be using Gauss-Seidel, value decomposition kind of things. But the rest of the things will be the same. And whenever we are going to handle the software, make sure that in background it happens in this fashion. So in later stage you can determine this, once you know the deformations, you can quite easily determine strain in the matrix, strain in the element. And once you know the strain, you can determine the stress by Hooke's law, that stress is directly proportional to strain, and you know the E value, you can determine the stress, and you can determine force or reaction in the element and kind of things. You can do it quite easily. So this is what the way we can handle this FEA part. Now I will take one simple example. I will now take one simple example into the FEA solver. I will take one single blank window. Okay. We'll start with a simple problem. So you may be having some bookshelf or something. That bookshelf, I will start with an FEA analysis and kind of things. We'll first of all define a problem. So bookshelf is nothing but a device which is having this shape. This is what the shape, having some thickness. Okay. And you want to have these 2 holes to fix onto the wall. This will look like this. This is going to fix it here. This is another fixing, and you are going to keep the books onto this. Ultimately, the problem with the manufacturer is that, so what are this thickness? Okay, he want to define this thickness such that weight is optimized. Weight is optimized. Most important, you want to optimize the weight. Ultimately, when we are going to optimize the weight, the stress in this entire component should not exceed 150 or 120, I can say 120 Newton per mm square. And he want to manufacture this for maybe 100 pieces per day. Okay, and material it is used is steel material it is used, and you know that cost of the steel is somewhere 250 rupees per kg, and you want to determine how much amount of, initially it was started with a 5 mm thickness. You want to reduce this thickness such that it should not exceed the stress value 120 Newton per mm square, and and also it reduces the weight of it. Okay, so you want to do this entire analysis, that is what the case. So before doing an analysis, this is what in a vaguely it is defined. First of all, we will define the dimensions for this. I'll assume it is in a 300 by, this is again 300. Okay, this is what in a 300, and this third is also dimension is 300, and the entire thickness is the same, t is equal to 5 mm. I'll start with this model, and I will now optimize this. How can I do it in ANSYS, and how this ANSYS will help us to do this all analysis. Okay, we'll keep this definition as it is, and we'll look at the ANSYS. I'll show you this ANSYS window is a very simple one. We'll do it in very simple static analysis. In static analysis, so here you can, this is what an entire window for ANSYS. What that window, this is what it is, a project schematic. I think you can see my screen. Is my screen is visible to everyone? Yes, you can answer. Yeah. So this is what on a project schematic, and left side you can see, and so many options are available. One is design assessment, electric, explicit analysis, so many options are there. So you want to do a simple static structural analysis. You can bring that static structural and drop it here. Okay, that's a simple way, because in previous way that ANSYS simulation was one of the very complicated simulation, but nowadays they made it very easy one. In this, it will take time because my PC got small, somewhat slower, maybe use. So here you can see there is an engineering data. It is defaultly taking material property, then geometry, then model, then setup, and then solution, and then results. So on right side you can just observe engineering data. There is a green check mark, then question mark, all the question mark. So green check mark indicates your data is completely filled and it is up to the mark. And if your data is not filled completely, then it will show you the green check mark. And if your solution is not perfect enough, or maybe having some error, it will create a red mark onto this. Okay. My PCs will take much time. अरे यार कितनी बड़ी already I removed all temp files. So in this case you can just look at different tools are there. There is a linear buckling tool, then structural analysis tool, vibration analysis tool, then there are certain tools like modal analysis is also there, then random vibrations are also there. Okay, so all these tools will be used for analysis. So there is one more interesting tool is called as a rigid body dynamics, where you can design your mechanism, you can do this mechanism analysis or kind of things. Here there is a temperature analysis, that is a transient structural analysis, transient thermal analysis, and there are certain more tools are also available here. So you can do an optimization, you can do a surface response analysis, so many things you can do it. So here you can just look at, this is what in a design model, where you can create your model. So here it's in a simple, I can just click onto this XY plane, right click onto this, I'll say it is going to look at the face, and then I will go into the sketching. I'll start sketching within a simple rectangle. This is one rectangle I created. Okay, so I need to give a thickness for it. So then let it be complete. Then I have another rectangle I create. Okay, then I will give a dimensions for it. So this is what in a dimension, this is another dimension. Then I'll skip this. So will give you one more dimension, that is vertical dimension. This is another horizontal dimension I need. This is what in thickness. Okay, and what are this part I will in between, I created a two rectangles, that's what I need to trim this in middle part. Okay, so then I can go on giving these dimensions quite easily. Here it is, when I click onto this it will highlight. So this dimension is a 5 mm, as we decided in the initial phase. This dimension is also 5 mm. This dimension is how much? We decided it is in a 300 mm. And this dimension also it is in 300 mm. Okay, so now you can visualize this complete model like this, and then go back and then say it is an extrude. Okay, then extrude with an it was initially I not selected a unit, so it is taken as an emitter as a unit. Here you can select a name. So this kind of a small mistake we may do it, so we need to just remove this once again and okay, and just so here it is a, I'll just put 5 mm here. Here it is in a 5 mm. Then here it is in 300 because it is converted into meters. This is again 300, and then I can now say it is in a, look at the face. So this is what in a shape, and then you can say it is an extrude. Okay, and this extrude I'm going to give it a depth of 300 mm, and then say it is in a generate. It will generate a component for you. Okay, so this is what gonna component it has created. Okay, so once we create a component, and there is one more facility in the ANSYS, that is what it is called as a parametric design. So here in our design, basically parameter is what? Your thickness is your parameter. This is what in the thickness you want to vary, and for that we want to define parameter as in a thickness as in a parameter. I'll go back into the sketch. I'll define this parameter as one of the thickness. Okay, and then I will select this as in one parameter, and I will give the name as in a t for it. So this is what in t I have given name. The same I can now define another parameter t for next one. Let it complete its process. It may take too much time. Okay, so then we have defined another one, the same value I am going to give the t because both are the same. Okay, you can provide an equation also here, don't worry about it. Now these two parameters, this t parameter will be used for optimization purpose in later stage, because you don't want to change any of the other dimensions, but you want to concentrate on only one single t as one parameter. But you can go for multiple such parameters also. Okay, then once here previously it was an question mark, it is now removed to the green check mark. Okay, then you go into the model. Then in this model, what we are doing, what are the model we created? We are, one thing I missed it, I not created in a holes onto this. Okay, I will. Okay. So we are going to fix it at one part, and then you are applying the load onto this. You are going to mesh it. Once we create a mesh, and then we are solving it. That is what we can do it. So if you want more information of such tutorials, already I created in the FEM class, because I was teaching this course in our college. I'll put one. I will show you one website where you can get, that is YouTube. All the videos you can get, all those videos on YouTube channel. So that I created my own channel. You can just search on the YouTube. That is Suhas Deshmukh. If you search it, you will get that channel. Okay. So there is one question I will take up and let it open. You can put up your questions on chat box. I will just answer few of those. So how to calculate terminal velocity? Calculate easily using first order solution. Okay. So I think you have seen in a terminal velocity how it is calculated. Terminal velocity is nothing but a maximum velocity. Okay. Where your both the forces become zero, and sum of the both the forces, that downward force and upward force, is the same, and that is what it is called as a terminal velocity. And simply you can get the formula, either you can solve it by first order equation or any other. If you have any question, you can put up those questions into your chat so that I can answer those questions. Now you got on a plate. So here I need to provide holes. I forgot to put the holes onto this. I will not again go back, it will take too much time. Instead of that, I will fix up this entire plate onto this end. Okay, this end. Or I can now do on a simple. Anyway, we will just modify that also. We'll just look at. Now the symbols are going to change it. Just look at here. It is a yellow mark, one question mark. So many things are there. So in this case, we can now apply the forces. Right click onto this. So I will put the force onto the edge. So this is the edge on which I am going to put the force. I can put this force and sorry, it is wrongly selected. There are multiple options onto this. So this is fixed support. It is I need to select it. So we'll just previously for that I will just open up on a model and I will provide a hole onto this. This is the plane on which I want to do the hole. Look at the face. Provide two holes onto this. So hole I will take as horizontal holes. I will not take vertical holes. Why horizontal holes? There is you can answer that question. Why I am going to take horizontal holes? Don't give an answer that I like it, but the answer there should be a technical reason for it. So this dimensions I will put at 25. Actually hole it should be larger one. This is 25. This is I will put at 200. Here I will put it 50. No, I will put it 100 here from this end, and here it is 150 I will take. I am keeping everything symmetric. Keep in mind why. You can answer on the screen. So I need to again go into the extrude part of it. So in this extrude, instead of add material, what I have to do? I have to remove the material or cut the material, and then I can tell how much amount of cut I want to do it. What is the extent to which I want to do it through all. You can say it is in a generate. Okay, and then close it. Okay. So once you close this, then again you go into this model. It will ask you whether you want to reread it. It will reread that information and it will open up the model whichever it is modified just now. Okay. So already it is open. It will take a few minutes to open up. So meanwhile you can answer my question. So why there is I took it horizontal holes? Yes, anyone is there? Why not vertical holes? Yes, put into the chat. Anyway, you people are not interested, I think. So these holes, I'm going to fix it. Now I can already I applied the 4. I need to fix these holes. Okay. I can now select in most of the assemblies, you may have multiple holes onto this, like maybe a 50 or something, and each and every one hole you are going to check it. So in that case, you can use some macros into this. Okay. In this macros, you can just go into the PC, then C drive, then ANSYS, program files, then this, then EISOL, then somewhere I think design pages, design space, then DS pages, and then there is a macros, and then I need to select by size. There are so many macros are there. Then select by size, so automatically next hole also will be selected. So likewise, if you want to select within a single click, maybe 20 holes or something, quite easily you can do it. Then now you can apply the force onto this. This is what the force you want to apply. So that force you want to apply maybe 250 Newton. Okay. 250 Newton means 25 kg load I am going to apply it. Then you want to observe the deformations. Okay. So you can apply the deformation. Also you want to determine one miss stresses. Can you tell me why this one miss stresses only it is mostly used for analysis? That is equivalent stress or something. Okay. So we have started simulation with the initial starting parameter, that is the thickness as an input parameter for my model. Output parameter I need to define it. So I can go into the geometry. In the geometry I can click onto the solid, and here there is a bonding box, then properties. I can just go into the properties. Here you can get the weight of it. So volume is there, and here currently your entire plate weight is 6.9 kg. Okay, this is what an output I want to measure it. So I can now check this box which will connect to the output. That is what the way you can do it. Another one, you want to now get the maximum deformation. So here it is in a maximum results I want it. Then same also I want to do it for this equivalent stress also. Okay. Then you can tell him to solve. Each and everything is ready now. Yeah. Meanwhile you can answer, or you can put your questions on the chat. No one is giving an answer, I think. Okay. So after solving this, you will get two values. One is deformation, another is a stress value. So stresses will be, obviously it will be in a maximum at these holes, around the holes. Okay. So it will take time because it has to divide it, it has to mesh it, it has to apply the boundary conditions and apply the forces on it. Okay. Yes, any questions? So we got the maximum stress at this location and this location. Okay. So what is the maximum stress we got? It is an MPa. We'll just get into the unit, proper unit, so it is 43 something. So it is on lower side. maximum stress is 120 we are expecting. What we can do at, we want to now reduce the thickness. Reducing the thickness will increase the stress. So what is the maximum stress you can reach? 120 Newton something. Okay. So now you can just go back to your Windows main window. Here there is one more tool come into the picture. So that is a parameters. In this parameter now you have defined input parameter t as in one of the parameter. Okay. So here it will tell you t is my first parameter. Then output parameter is 6.9 kg, weight is one parameter, deformation is second parameter, and your stress is your third parameter. Here you can define metric something, so it will tell you the Newton per mm square. Okay. Okay. So then you can now go on changing the values of this here itself. I can go here, it is on 4.5. Okay, sorry, 4.5. Then I can go for 4.0. Then I can go for 3.5. Then 3.0. Then 2.5. Likewise, I can go for any model. So when I'm going to say it is update all design points. I will just go one more, that is 2 mm thickness. Okay, and then I will say update all design points. So what it will do, as it is going to create this model, it will go to the boundary, that is a mechanical, it will apply the boundary conditions, and it will tell you, it will update this entire table, and then you can now identify which design is going to be the best for us. So it should not be, value should not be somewhere 120 Newton per mm square, and below that value you can select, and that is nothing but your final design. That is what the way you can do in a crude optimization of this using an ANSYS. This is for today's session. Okay. So now I think I finished my work. If you have any questions till the time, let it get simulate. We'll have a few questions and then we'll close up our session. Yeah. Any questions, sir? Sir, are you there? Yeah. Directly ask. Okay. So they are more reluctant to ask the questions, I think. There will be another way around also. So I will show you one YouTube channel where you can go and get all such videos. So you can search on the Google YouTube my name, that is Suhas Deshmukh. So I created it is